This video gives examples of negative feedback amplifiers, including the unity gain buffer. It corresponds to sections 19.2 and 19.3 of the Applied Analog Electronics textbook. Let's start out with a specific design problem. For example, let's try designing an amplifier with a gain of 23. That is to say, we want to have the out minus Vref is equal to 23 times the in minus Vref. And here we're going to ignore the input offset and any limitations we might have from the gain bandwidth product. So we're just looking at ideal amplifiers here. In the real world, we would, after doing this design, take a look to see what the effect of input offset and gain bandwidth product and any other limitations that the amplifier has on the design, to see if we have to redesign something in order to take account of these imperfections. But we usually start by designing as if our amplifiers were perfect op amps, and quite often that's good enough and we do not have to make any corrections to that design. Alright, so how do we go about doing this? Well, first thing, we're going to need to have an op amp, and it's going to have to be configured as a negative feedback amplifier. And notice that even though our gain here is positive, the feedback is to the negative input. The feedback is always to the negative input. Slogan of the class, no positive feedback. All right, but because we want positive gain here, that means that V in has got to come in on the positive input of the op amp. And V out comes out here, and we'll need to have Vref coming in on that input. So this is a non-inverting amplifier. Gain is positive, 23. So what was the gain of a non-inverting amplifier? Well, if this one is Ri and this one is Rf, the gain of the amplifier is Rf over Ri plus 1. And that gain formula for non-inverting amplifiers, we derived it in a previous video, but it's worth memorizing. You use it all the time. If you have to rederive it each time, you'll be doing very, very slowly. Okay, so that's the gain. We want that to be 23. What does that tell us? Well, Rf over Ri is 22. Now, that doesn't tell us what these two resistors are, but it tells us what the ratio of the two resistors are. And it turns out we can design this amplifier with any pair of resistors that have the appropriate ratio. But if we make Ri and Rf very small, then the voltage difference between Vref and Vout, notice that there's going to be current flowing through those resistors. And that current will get very large if the resistors are very small. So in order to reduce the load on the output, and in order to keep from taking too much current from Vref, we'll make those resistors big. How big? Well, the other problem we have to worry about is that there's parasitic capacitance floating around in our circuit. A few picofarads here, a few picofarads there. And so if we make the resistors huge, we run into the problem that we have the capacitors starting to matter more than the resistors. The other problem we have is that we're pretending that this is a perfect op amp, and so it takes no current at all at the input. But op amps aren't perfect. They do take a tiny, tiny current there, and if your resistors are huge, that tiny current results in a voltage change. So, rough rule of thumb, we try to keep our resistors between a kilo ohm and a mega ohm. And for something like this, bigger is generally better because we don't want to be taking current from Vref. We want to have a high input impedance here. We don't want to be taking current from the amplifier to be going to Vref either, so everything's going to be big. We want to be up near the mega ohm, which is sort of our rough rule of thumb as our upper limit. Now, 22 is a nice ratio for us because 2.2 is one of the things in the E6 series even, so these are very common resistors. We could do something like 220 kiloohms, and then a 22nd of that, 10 kiloohms. Okay, we're basically done. The only thing that we need to be aware of is that we can be taking current from VREF. Not a lot of current, but we can be taking current from VREF, so VREF has got to be coming from something that's capable of providing current. A simple voltage divider would not be a good choice because the voltage would change as the current changed, and as V input changes, this node here at the negative one, remember that in a negative feedback amplifier, the negative input here is held to being very, very close to the positive input. So this voltage is going to vary just as Vin varies, and so the current through this 10 kilo ohm resistor is going to vary, and we don't want to have current, particularly not varying current, being taken from a voltage divider that changes the voltage, no longer behaves as a constant reference voltage, which is what we wanted it to be. So we need some way to provide current. We basically have only two things that are capable of providing current in our current repertoire of devices. There's a power supply and there's an amplifier. Power supplies are kind of expensive. We generally don't put in power supplies unless we need a lot of current. And generally for VREF, we're going to be hooking up to things like this where the current demands are going to be pretty modest. So we're not going to need a full power supply for it. Also, a clean power supply, one that doesn't have any fluctuation, is kind of expensive. So what we would like to do is take VREF from an amplifier. Well, that's nice. We can do that. But what would we want at the input for the amplifier? Well, the nicest thing to do would be to have something like a voltage divider that sets what VREF is. So come over here and draw what we would like VREF to be generated by. So let's say we wanted this to be halfway between our power rails. So we would have whatever our power rail up here is, let's say arbitrarily 5 volts. Pair of resistors here going to ground. And that's what we would like to have VREF be, with these two resistors being the same. Again, we don't want a lot of current going from 5 volts to ground, not doing anything, so we might want to set this thing to be big numbers, maybe a mega ohm and a mega ohm. Okay, so now this is going to be 2.5 volts, except for that anytime the 5 volt has some noise on it, well, the 2.5 volts is going to have some noise on it. And we'd really like our VREF to be as constant as we can make it. So let's add a capacitor here. This now acts as a low-pass filter. If we put something like 1 microfarad here, then we would have the Thevenin equivalent of this voltage divider would be half a mega ohm. So we would have a time constant of half a mega ohm times 1 microfarad, or half a second. And that would mean a frequency, so if we have that half second, multiplied by 2 pi, and invert, and we have about 0.32 hertz as our corner frequency. So now we've got something that filters out all sorts of high frequency noise on the power supply and gives us a nice constant 2.5 volts with only very small fluctuations if this has fluctuations. But we can't take current from this because this is, Thevenin equivalent was half a mega ohm. If you tried to put that in series with the 10 kilo ohms here, this wouldn't be behaving like 10 kilo ohms anymore. It'd be behaving like half a mega ohm plus 10 kilo ohms, and we wouldn't be getting the gain we want. So how do we get something that can provide this constant 2.5 volts with current? Well, we need an amplifier with a gain of 1. We want the output to be the same as the input, but capable of delivering a fair amount of current. So how do we get a gain of 1? Well, it's going to again be a non-inverting sort of amplifier, but we can do a bit of a trick here. we can put this into the positive input, and then for the negative input, we can just put a wire from VREF back. So this is a resistance of 0. And we have an infinite resistance to whatever our reference voltage is. What does that mean? Well, that means that the gain of this thing is going to be RF over Ri plus 1. RF is 0, Ri is infinite, so 0 over infinity is just 0, plus 1. The gain is going to be 1. And that means the output here is going to be the same as the input. And this is the way that we can generate VREF. We got a current here. We can have as much current as this op-amp is capable of delivering. And we have it at the constant voltage that we've selected with this low-pass filter from the power supply here. And this is a very standard sort of circuit. We'll be using this one over and over again in this course. It consists of a voltage divider and capacitor here to get a constant voltage. And this other device here is called a unity gain buffer. It's unity gain because it has a gain of 1. And a buffer is an amplifier that isn't trying to change things. It's basically just providing more current capability. So the unity gain buffer is a very, very common building block. It's gain of 1. And voltage dividers, we've done that quite a bit, adding capacitors to make it into a low-pass filter to get rid of high-frequency noise. This is our standard VREF generator. So there is our full circuit, not only containing the get this whole thing's there now, V out minus VREF, having a gain of 23, but generating the VREF to be in the middle between the two voltage rails, 5 volts and ground. Okay, let's look at one other problem then. What if we want a negative gain? Say a gain of minus 1. Can we get a gain of minus 1? Well, I'll just start a new sheet of paper here. We're going to again have negative feedback amplifier. And you may have noticed that I sometimes put the plus on the bottom, sometimes put the plus on the top. There is no standard convention that it's one or the other, so you always have to label which one's plus and which one's minus. They always have to be there because there isn't a standard convention about top and bottom. All right, to make this thing a gain of minus 1, I have to have a negative gain, an inverting amplifier, so I need the inverting configuration. And in the inverting configuration, the input has got to come in on the side that goes to the negative 1. Now notice it's not going directly to the negative 1, it is going through resistor to the negative 1. This was, again, Ri, and this one was Rf. And we now take Vref in the other one. So we're trying to get V out minus Vref equals negative 1 times V in minus Vref. All right, what is the gain of an inverting amplifier? Well, that is another formula you're supposed to memorize. We derived it before. It's just minus Rf over Ri. So if that's gain of minus 1, basically that's telling us that Rf equals Ri. And again, any pair of resistors will do. But we have the same limitations as before. We probably don't want to take a lot of current from V in. We probably don't want to take a lot of current from the output of the amplifier because any current we take from the output of the amplifier is not going to be available to drive whatever's out there at V out. So again, we probably want the resistors to be pretty large. But not too large again, because we can have things like parasitic capacitance and tiny input currents on the amplifiers and stuff. And so, rough rule of thumb, sticking between a kilo ohm and a mega ohm, we could make this 1 mega ohm and 1 mega ohm, and it would probably work. Okay, so we've now looked at positive gain amplifier, gain of 23, unity gain amplifier, a very nice special case and one that is well worth memorizing, and a negative gain amplifier with a gain of -1. Now notice that this inverting formula can go anywhere from 0 to negative infinity. The non-inverting one is limited to +1 to infinity. For a gain between 0 and 1, you can't really do it with just one of these two amplifier designs. Could do it with a voltage divider, because the voltage dividers that we've had in the past basically had gains between 0 and 1. So if you want a gain between 0 and 1, use a voltage divider. You want a gain bigger than 1, use a non-inverting amplifier. Want a gain less than 0, using an inverting amplifier. If you want a gain between 0 and 1, but you need to take current from it, use your voltage divider, and then add a unity gain buffer. Okay, I think that's probably enough for examples in this video. There's some exercises in the book for you to try doing your own.